Hey everyone, and welcome. Today we're going to dive into something that's at the absolute heart of all science: errors and uncertainties. Now that might sound a little intimidating, but trust me, it's actually the secret sauce that lets scientists trust their own results, and for us to trust them too. So let's get right into it. So let me kick things off with a question for you. When you measure something, anything, say the length of your desk, can you ever get the perfect 100% exact value? The answer, and it doesn't matter how fancy your tools are, is always going to be no. And you know what? That's not a failure. It's just how the real world works.
You see, in science, the goal isn't to chase some impossible idea of perfection. The real goal is honesty. It's about being crystal clear about what you measured and, just as importantly, how confident you are in that number. What we're talking about today is the exact toolkit scientists use to be that honest.
Okay, first things first. Before we can fix problems, we need to learn the language. When scientists talk about how good their measurements are, two words pop up all the time: accuracy and precision. So let's break down what they really mean. Now, accuracy and precision. We tend to use these words like they mean the same thing in everyday life, but in science, they are worlds apart. Accuracy, that's all about how close you are to the true value. Are you hitting the bullseye? Precision, on the other hand, is all about consistency. It's about how tightly grouped your measurements are, even if they're nowhere near the bullseye. The best way to get this is to think of a target. So look at the image on the left. All the shots are clustered tightly right in the center. That's the dream, right? It's both accurate and precise. But now look at the target on the right. The shots are still in a nice tight cluster, so they're very precise, but the whole group is way off center. That's high precision but low accuracy. You're being consistently wrong. And here are the other two combos. On the left, you've got shots scattered all over the place, so the precision is terrible. But if you were to average them all out, the center of that scatter is right on the bullseye. So weirdly enough, that's accurate, but not precise. And the target on the right? Well, that's just a bad day at the range. The shots are all over the place and nowhere near the center. That is neither accurate nor precise. So how do we actually put a number on this doubt? Well, that's where uncertainty comes in. Absolute uncertainty gives us a simple plus or minus range. So if we measure something as 50 millimeters plus or minus 1, we're really saying, hey, the true value is probably somewhere between 49 and 51. Then you have percentage uncertainty, which is super useful because it tells you how big of a deal that error actually is compared to your measurement. We know our measurements aren't perfect, but the really important question is, why? What's causing these issues? Well, turns out we can usually diagnose the cause and put it into one of two main categories: systematic errors and random errors. Getting the difference between these two is absolutely key to improving any experiment. So, here's the bottom line. Systematic errors are consistent, predictable problems. They push every single one of your measurements in the same direction, away from the true value. That kills your accuracy. Random errors, on the other hand, are those unpredictable little wobbles. They make your results scatter around an average value, and that messes with your precision. Let's dig into systematic errors for a second. The thing you have to remember is that these guys are sneaky. Because they're so consistent, you can't just take more measurements and average them out. You'll just get a very precise average of the wrong number. A perfect example is a zero error. Think of a kitchen scale that says there's 10 grams on it before you've even put anything on. And here is a fantastic real-world example with a micrometer, which is a super precise tool. What you're seeing is what happens when we check its 0 point. See how when the jaws are totally shut, it's not reading 0? It's reading plus 0.12 millimeters. That's a systematic zero error. It means every single measurement you take from now on is going to be 0.12 millimeters too big, unless you remember to subtract it. Okay, now let's talk about random errors. These are all those little variations that are kind of out of your control. Maybe the needle on a dial is flickering a bit, or your reaction time with a stopwatch is slightly different each time. But here's the cool part. Unlike systematic errors, you can fight back against random errors. And the magic trick is simple. Take a bunch of readings and average them. The random highs and lows start to cancel each other out. A classic example of a random error is something called parallax error. You've definitely done this. It's what happens when you look at a ruler or a car speedometer from different angles. As you can see in the diagram, depending on your line of sight, the reading seems to shift. If your head is in a slightly different position for each reading, you're going to introduce that unpredictable scatter. So, now we can speak the language. We know what accuracy and precision are, and we can diagnose the two main types of errors. It's time to put all that knowledge into action. This is all about making smart choices, from picking the right tool for the job to knowing how to handle uncertainties when you start doing math with your numbers. This is so important. You have to match the tool to the task. I mean, imagine trying to measure the thickness of a single piece of paper with a big meter stick. It's just not going to work. The uncertainty in the ruler is way bigger than the thing you're trying to measure. For that job, you need a high-precision tool like a micrometer to get a result that actually means something. Okay, this is where things can get a little tricky, but it's crucial. What happens when you use your measurements in a calculation, like finding the area of a room? Well, the uncertainty comes along for the ride. There are two basic rules you have to know. Rule 1. If you're adding or subtracting measurements, you add their absolute uncertainties. It's kind of like a worst-case scenario. The errors could stack up. But Rule 2, if you're multiplying or dividing, you add their percentage uncertainties. This makes sense because the relative size of the error matters more in these cases. Following these rules is how you honestly report the uncertainty in a calculated result. All right, theory is one thing, but the best way to really get a feel for this stuff is to see it in action. So let's walk through a few real-world examples and put our new skills to the test. Let's start with reading these instruments. First up, the micrometer. The scale is showing a reading of 15.62 millimeters. But wait, we have to remember that systematic zero error of positive 0.12 millimeters. So to find the true length, we have to subtract that error. 15.62 minus 0.12 gives us a corrected length of 15.50 millimeters. Simple. For the vernier caliper, there's no zero error mentioned, so we just read it directly, 5.53 centimeters. Okay, your turn. Here's a very typical problem you might see. You've got a micrometer with a positive zero error of 0.02 millimeters. You then use it to measure an object and the reading is 12.38 millimeters. So what's the actual corrected diameter? You got it, because the zero error is positive, meaning the scale started too high. You have to subtract that error from your final reading. So you take 12.38, subtract 0.02, and you get the correct diameter of 12.36 millimeters. See? Once you know the rule, it's straightforward. Okay, ready for a level up? This one's a bit more involved. Digital instruments often have this two-part uncertainty. This ammeter has an uncertainty that's a percentage of the reading plus a fixed number of digits. So for a reading of 2.64 amps, what's the total uncertainty? The trick is to just tackle it one piece at a time. First, let's figure out the percentage part. 1.5% of 2.64 is 0.040 amps. Okay, now for the two digits part. That refers to the last decimal place, so that's an uncertainty of 0.02 amps. To get the total uncertainty, you just add them together. 0.040 plus 0.02 gives us 0.06 amps. So the final honest reading is 2.64 plus or minus 0.06 amps. Okay, let's step back from the numbers for a second and think conceptually. Imagine a super simple task, measuring a pencil with a plain old ruler. Can you think of one possible systematic error and one possible random error that could happen? And more importantly, what could you do to reduce them? These are perfect answers. For a systematic error, a really common one is a worn-down end of the ruler. If you always measure from that damaged zero mark, every measurement will be consistently off. The easy fix? Don't use the end. Just start at the 1 centimeter mark and remember to subtract it from your final reading. And for the random error, parallax is the classic culprit. The solution is just good technique. Get your eye level with the marking and look straight down, perpendicular to the ruler. All right, you've been doing great. You've learned the concepts, you've walked through the practice problems. Let's wrap things up with a quick final challenge, a typical exam-style question, just to make sure all this knowledge is locked in. Here it is, nice and clean. You've measured something to be 20 centimeters, and you know the absolute uncertainty is plus or minus half a centimeter. The question is simple. What's the percentage uncertainty? And the answer is 2.5%. The calculation is just the absolute uncertainty, 0.5, divided by the measurement itself, 20. Then you multiply that by 100 to turn it into a percentage. Bam, 2.5%. So, what's the big takeaway from all this? I want you to leave with this thought. Every set of data you collect tells a story. But without understanding and reporting the uncertainties, that story might not be the whole truth. Acknowledging errors isn't about admitting you failed. It's about making your scientific story stronger, more honest, and ultimately more powerful. So the real question is, how will you make your story true?